All right, screwed that up. There we go. Let's go check some homework. The homework is on inverse functions, finding inverse functions. So I'm hopeful that we are able to determine if it has an inverse, and if it does, be able to find that inverse. Here's the first one. I want to talk through this one just a little bit. It said, here's your function, f at x is a negative x. So it says, whatever you put in for an input, you always take the opposite of the input. So what happens when you take a negative 4 and you take the opposite of a negative 4? 4. It gets paired with a 4. What happens with a 3? The negative 3 goes to the 3, the negative 2 goes to the 2. So you end up with an arrow graph that looks like this. Now from this arrow graph, we're asked two questions. Is it a function? And then does it have an inverse if it is a function? So, a function, first of all. Does every input get paired with exactly one output? Yes. So then you'd have to say, yes. Is every one of these outputs unique? Yes. Then it's a one-to-one function, so it has an inverse. Those are the two qualifications I look for every time I look at an arrow graph or in set-of-ordered pairs or even a graph of a function. Question B, does this graph look like a graph that would have an inverse function? Now, I already have this line on here, so it should be reminding you we should run what kind of a test on it to see if it has an inverse. What we're doing is we're testing for uniqueness of these answers. So is every single answer on there unique? Yep. You go down to your second graph in question B. Is every one of these unique? And this is just frustrating. No. There's a bunch of outputs here that are not unique. So does it have an inverse? No. Finding inverse rules. Here's answers to your inverse rules. See if this sparks any debate or questions. I believe we should be getting these two. F inverse is 2x plus 4. G inverse is 0.5 divided by x plus 2. Follow-up questions. Karen.
Can you go over I, please?
Go over I, the first one.
Yeah, I got the second one.
So I, the first thing that we are asked to do is always replace your function notation with y. So y equals half of x minus 2. Now, what do we do to find the inverse? Right. When we do the inverse, we're switching the roles of the input and the output. The inputs become your new outputs, and your old outputs become your new inputs. So the y's go in there. Solve it for y. What's the first thing you remove? What's the first thing you remove? The 2. How do we move it? Add 2. So x plus 2 equals 0.5y. So now we could divide by 0.5, or we can recognize that 0.5 is the same thing as a half. And how do we get rid of multiplying by a half? Multiply by its reciprocal. So multiply this times 2. So that's where they got the 2x plus 4. Which, I'll be right back to you. If we finish this, that was f inverse of x. Say it again.
Could you do it the other way, like x plus 2 over 0.5?
0.5? I wouldn't prefer it, but it isn't any different.
Like, would you kind of run?
I wouldn't be very happy with it.
Why?
Because you're putting the decimal in the denominator, we can do better. How can we do better? Recognize dividing by 0.5 is divided by a half, it's multiplied by 2.
You'd like us to do that every time?
I would, actually. Yeah, it's a preference. Is it equal? Yes.
So mine was right.
Right. Your format was probably a little different. Which ones of these graphs actually have an inverse? Does graph 1 have an inverse?
This?
Yes, passes the horizontal line test. Is graph number 2? No, it does not pass this horizontal line test. Does graph 3 pass it?
No.
Some people are saying no, and some people are saying yes. This is a yes. The only reason I think people were looking at this one, right?
Yeah.
Right at 0. But this graph, this is just a matter of zooming in. If you zoom in, zoom in, zoom in, this graph is always increasing. So it's a bit unfair. But if you know the principles and the things that are happening with the cubic function, it's always going up. So this is, yes, it has an inverse. Zoom in more.
I did and then it didn't show up.
It's just a matter of zooming. I promise you, it's always different.
What isn't it one of those ones that goes like this?
Then no, not if it never has a max or a min. Does this graph ever have a turning point? A max or min point?
Yeah, but what is the max?
Does it have a turning point? This one doesn't, so therefore it's going to have an inverse. You're talking about a graph that does have a turning point. Now, is it going to have an inverse? No. Even if a graph has one turning point, is it going to have an inverse? No. So every graph with a turning point doesn't have an inverse function, unless we restrict the domain. Does graph number 4 have an inverse function? Yep. You apply this horizontal line test to it, does it ever touch the graph more than once? We're verifying that every output is unique then. Every output on that one isn't unique, it hits it twice. And in the final one, oh, nope, this is not the final one. Number 7. I would prefer, again, it's a preference, this answer over the other one for your inverse of f. There's not a lot of discrepancy for the next two, and I would prefer this one over their other alternative on letter D. There's 4 more examples of trying to find the inverse function, going through that 4-stage or step process. Do you need any assistance with these?
Okay, so for like A and D, like the signs are messed up like that I had. Why is that?
The signs are messed up.
Yeah.
Probably they didn't really do the inverse then. We'll go look at A or D. I don't care which one. What do you want?
Do A.
A. So the first thing we do is replace the f of x with y. Whenever we find the inverse, we're turning the question around, so our old inputs become outputs, outputs become inputs. Here and here. X equals 4x minus 5. When you said when you said your signs were switched, I'm wondering, how did you undo subtracting? I did it again. Stop talking. Think. Now talk.
X plus 5.
Sure you do.
Why would it?
You do. X plus 5 equals 4y.
Oh, and I just screwed up. Okay.
So then you divide by 4.
I got it.
Did I hear someone else have a question on one? C. Do you see that C, its inverse wasn't any different?
Yeah, exactly.
Isn't that crazy? H at x is 5 over x. This bugger here is a butterfly graph. Does it pass the vertical line test? Is it a function to begin with? Does it pass the horizontal line test? Are all your outputs unique? So it has an inverse. So to find the inverse, y equals 5 over x. Then we switch the roles of x and y, so x equals 5 over y. Then we got to get the y out of the denominator, so x times y is 5, or y is 5 divided by x. This is your inverse, h inverse of x. Okay? Now let's test this. It's one of those unique functions where its inverse is identical to the original function. So if we take h at 10, I want to plug 10 into this function. That means it's 5 over 10, which is a half. So h at 10 is a half. The inverse function is supposed to take your old output and bring you back to your old input. So h inverse at x says take your old output, which was a half, put it into your inverse function, which is 5 over x, so 5 divided by 1/2. Does it bring you back to your old input? So what is 5 divided by a half equivalent to? 5 divided by a half, same thing as a reciprocal. 5 times 2 over 1, or 10. You put in a half, it gave you 10. You put in a 10, it gave you half. Did it switch your roles? No. Every once in a while you run into these goofy deals where, hey, that's the same. And finally, number 8. To determine the price per gas, you take $3.95 times G. Every time you pump any amount of gas, is there only one price that goes with it? So it's got an inverse. For every input of gas that you pump, there's one price that you pay. It's a unique price, so it has an inverse. They didn't write their inverse using inverse language. It is your price divided by 395 would give you your number of gallon that you bought. If you followed our procedure, you would have had P inverse at G equals G divided by 395. Does that match anybody? That's what we were asked to do. For the second one, to figure out how many mathematics classes you need, you take your number of students divided by 20. So if I know the number of students divided by 20, every time I divide by 20, does it give me a unique number? Yep, so that means it's a one-to-one function. So how do we undo it? How do we reverse it? Take 20 times m will give you number of students. If you did it the way that I asked you to, you'd have m inverse at s would have equaled s times 20. And then area of a square is area side squared. Since it's the length of a side of a square, you don't have to worry about the negatives, because s squared, that a equals s squared, would be this graph, but this part never even gets considered because lengths can't be negative. Is this a graph of something that has an inverse? Yep. If you want to find the side length, if you know the area, then you take the square root of a. If you would have written it in this inverse notation, a inverse at s would equal the square root of s. Letter D, what do you know about daylight hours throughout the year? Sometimes it's less, sometimes it's more. When do we have more daylight? When do we have less? And what happens next year? So it's a cyclical pattern, and cyclical patterns follow either a sine or cosine curve, so we'd be doing something like this. More hours, less hours, more hours, less hours, repeated over and over again. This is a function, but it's not a function that has a inverse, because there could be multiple times we have the same amount of daylight hours, and that is a multiple choice. We don't want multiple choice on inverses. We are finished grading your homework. Put that to rest. Now let's get to our new stuff. Today we have to concentrate our efforts on logarithms. The reason we studied logarithms is that we are now to a point in our math career where we have to solve exponential equations. When you solve exponential equations, you will have to find a variable that's in the exponent. You do not have any means of doing that right now other than graphical or tables. We're going to come up with an algebraic way of doing it. So we're studying in Lesson 2 common logarithms and their properties. So the first little bit here is going to be a plug on reviewing exponential equations. Okay, so at several points in your study of algebra and functions, you have discovered relationships between variables that are well modeled by exponential functions. The rules of these functions have the form f at x equals a times b to the x. I underline that. This is really what they're getting at. This is the form of an exponential equation. If you have a good memory, you remember what A always told you about your situation. What does A always tell you about whatever situation you're dealing with? Okay? It's loss. So A is your start at value. It tells you how many bacteria you started, what's your initial investment that you started with, how much medication did you put in, how much radioactive material did you start with, those types of things. B, the bottom number here, the B always told you the rate of growth, or it could be the rate of decay. Coming back a little bit, repeat. What does A tell you? Start at value, and B is your rate of growth or rate of. Okay, something that's nice to know. If B is greater than 1, if this value of B here is greater than 1, you will always have a growth model. If B is somewhere between 0 and 1, then you always have a decay model. Now growth means you keep building bigger and bigger numbers. Decay means your numbers are going to get smaller. We'll look at some graphs here in a moment. Now we're going to look at 3 examples of things that we want to be able to solve here within just 2 days of instruction. Here's our first one. If a count shows 50 bacteria in a lab dish at the start of an experiment, and then the number is predicted to double every hour, then estimate the time when there will be 10,000 bacteria in the dish. It says you need to solve this equation. What does this 50 stand for? Your start at population. What did this 2 represent? Your rate of growth. And what did this 10,000 represent?
Final number.
The final number we want it to be. What are we after?
The T.
The T. And where is T located?
In the power.
It's in the power. It's in the exponent. Now we've done PEMDAS, and we have concentrated almost exclusively on addition, subtraction, multiplication, division. Now we're on the exponent level. What undoes addition? What undoes multiplication? And what undoes, we have had some exponents where we have exponents of 2. What if you have x squared? What undoes it? If you have x cubed, what would undo it? Cube root. What if you have the square root of x? What do you do to undo that? So you've been well versed on that. So now what do you do when it's x to a power of t, or it's 2 to the t? We have to know how to undo an exponent. What's going to undo an exponent? Logarithms. Just as you have been well versed in doing the inverse of adding and subtracting, the inverse of dividing is multiplication. What's the inverse of an exponent? Okay, let's try that again. What's the inverse of an exponent? We're going to learn logarithms. Logarithms help us find exponents. Pretty big statement. What do logarithms help us find? That's what we're going to use them for. Okay, so next example. Washington National Baseball Team was purchased in 2006 for $450 million. To find out how long it will take the value of this investment to reach $1 billion, if it increases at a fairly conservative rate of 5% a year, you need to solve this equation. Now, what in the world does this 450 stand for?
What it started at.
The start at value in millions. Why is it 1.05?
It's what you already have from 150 and just grows by 5%.
Okay, it's growing by 5%. You already have your 100% investment there, then it grows by another 5%. So 1.05. Remember, if B isn't greater than 1, it cannot do what?
Grow.
Can't grow. And we want to reach, what is 1,000?
It's supposed to be a billion.
Wow, that's a mind blower to me. If you had 1,000 stacks of $1 million, you would actually have what? A billion. That's incredible. 1,000 millions is a billion. What are we going to solve for? T. Where is T? And what are we going to need in order to get that T out of there? Logarithm. Nice job. You're getting it. Here we go. And last example. If 500 milligrams of medication enters a hospital patient's bloodstream at noon, indicates exponentially at a rate of 15% per hour the amount remaining active in the patient's blood stream T hours later will be given by this equation. The amount of dosage after a certain amount of time. What does the 500 stand for?
20 milligrams.
Your start at milligrams. Why is this 0.85?
It's subtract 15% from the 100.
Okay, if you remember, if it's 15% removed, what percent is left? 85%. You always use the part that's remaining. It's decaying because this number is less than, but bigger than 0. And again, we're solving for t, which is in the exponent. So to start off, here's my questions we're going to study. We're going to look at some things you should be familiar with, exponents. Exponent evaluations, we're going to look at some patterns. Anything to the power of 0 is always equal to what? We need to know this. How do we deal with negative exponents? Anything rates a negative exponent, what is it equal to? What does a graph of exponential look like, and then what does its inverse graph look like? So here's where I'm going to start this discussion. What is 2 to the third power equivalent to? 2 times 2 times 2, which is 8. Quick calculation, 8. What is 2 to the second power equal to? Good. What is 2 to the first power equal to? 2. I want to backtrack here. Let's go 2 to the fourth power. What if I needed 2 to the fifth power? They're doubling, right? So when we go this way, what are they doing? Halving, halving, halving. So what is 2 to the 0 power half to equal? You got to stay in that same pattern. So you take half of it. Half of 2 is 1. Okay, now let's go to these. What is 2 to the negative 1?
0.5.
I heard correct answers out there. I like a half. You'd have to divide by 2. What is 2 to the negative 2 equal to? 1/4. I'd have to take half of a half. Getting crowded, but what's 2 to the negative 3? 1/8. Now we just hit our first 2 questions. What is anything to the 0 power going to be? 1. How do we deal with negative exponents? What is the relationship between the negative exponents and their counterparts down here that are positive? That's typically how they're learned. Whenever you have a negative exponent, you reciprocate the normal exponent. So if it's going to be 2 to the negative 4, I simply know what 2 to the 4 is. It's 16, so it is. Okay, so now, have we raised the question and answered? What is anything to the 0 power? How do we deal with negative exponents? Reciprocate. On board? That's learning some exponent stuff. Now, what does the graph of an exponential function look like? These over here that we just got done is modeling an exponential growth equation, y equals 2 to the x. So we're going to look at what its graphs look like, or this graph looks like. So those are our axes. When you put in a 0 for an exponent, what did you get back out for the output? A 1. When we put in a 1 for an exponent, what did we get back out? 2. When we put in a 2, what did we get? 4. When we put in a 3, we got a 8, so it should be twice as high, so I'm going to estimate that. Okay. How about when we put in a negative 1? What do we get?
Half.
Half, so it only has to go up half. When we put in a negative 2, it was a fourth, and a negative 3 would be an 8. So it's got to come right along the axis, come up here. Is this bring back any memories of an exponential growth model? Something that's really important, I'm just going to bring it out right now. Does this graph ever go below the x-axis? So no matter what I raise 2 to, can I ever get a negative value back out? So 2 to some power will never be negative, right? Never be negative, can't. Okay, so that's what its exponential graph looks like. The next question I had up there, if this is what the exponential graph looks like, what does its inverse look like? Okay, I want to go back to the fundamental question of an inverse. What does an inverse do? Switches the domain and range. It reverses the roles. I'm really happy you got domain and range in there. It switches the domain and range. What it does is, so now I'm going to pick on a few things on exponents. When we do this equation here, I'm going to put it in function notation. F at x equals 2 to the x. It says you feed this thing an exponent, and it spits out a value which is called the new word antilog. You feed it an exponent, 2 to the 3rd power is 8. 8 is your antilog. All this stuff over here. We feed it a 4, it gives us a 16. We feed it a 3, it gives us an 8. That's what an exponential function is designed to do. Feed it exponent, spit out an antilog. So what is the inverse function going to do? If I do f inverse, what am I going to feed this thing? And what is it going to give me back out? If we feed this one an exponent, it spits out an antilog, then what's your inverse have to do? You have to feed it a antilog, and it's got to spit out a or an exponent. Am I making sense here with your concept of inverses? Inverses reverse the question. If this original function says, give me an exponent, I will give you the antilog, then what's the inverse have to do? Start with the antilog, come back to the exponent. Okay? So the roles get switched. The domains and the range gets changed. So every one of these ordered pairs, this ordered pair sitting right here, that was 3, 8. We're going to start with the 8, and we're going to come back to the 3. So we're going to start with an 8. Let's just assume that that 8 sitting out here, what's it going to give me back? A 3. I'm going to put the 3 up here. This one was the order pair 2, 4. But what's the inverse start with? Starts with a 4, it has to give you back the, so go to a 4, it's going to give you back a 2. This one, which was, put in a 1, you get a 2. So the inverse gives you a 2, or put in a 2 and it gives you back a 1. This one was the ordered pair 0, 1. So the inverse starts with the 1, gives you back a 0. This one was the ordered pair negative 1 half. So your inverse starts with a half, gives you a negative 1. This one was a negative 2, 1/4. So the inverse starts with a fourth, gives you a negative 2, and then negative 3 for an 8. So this is what your inverse graph looks like. This inverse graph is called your logarithm graph. You follow me? This is a log base 2 of x graph. What do we have to feed it? An antilog. What will it give me back? It will give me back the exponent I'm looking for. I just went through how to create an inverse graph very easily. If you can graph an exponential graph, how do you graph its inverse? Flip the ordered pairs around and graph them. If you graph them on the same axes, this is an always statement. It should always be symmetrical across that line, and that line is y equals x. Inverses will always be graphically symmetrical around the line y equals x. Which means if you flipped it and fold across that line, this graph should map onto that graph. That's why it looks like a butterfly. Okay. We're going to do the same thing with base 10 exponents. What is 10 to the second? 100. I fed it an exponent, it gave me back a what? What's that called? Antilog. What is 10 to the first? 10. What's 10 to the third? Thousands, or 1,000. Powers of 10 are really easy to work with. If you know your exponent, you know the number of zeros, or you know the number of decimal places. What is 10 to the 0? 1. What is 10 to the negative 1? 1/10. Or, now it's easier to kind of think of decimals too. What is 10 to the negative 2? 1/100th. Or as a decimal it is 0.01. Okay, nobody in soccer. What does this graph look like if we graph y equals 10 to the x? Sketch in the air, what's it look like? I got one graph. What's it look like? 2 graphs. So it starts really low, swings up here, goes high. Should this graph be steeper or flatter than our 2 to the x? Steeper, because every change has a factor of 10. Now, what's the inverse graph look like? I don't know how well I did at making them symmetrical, but they'd have to be symmetrical. All right. First mission accomplished. Second mission. I've got to get you to speak the language of logarithms. Here is your language. Definition of a logarithm says b to the x equals y if and only if log of base b of y equals x. Whoa, what's that mean? It means these two things say the same thing. They're written in a different language, different format. I would highly suggest that you jot this down somewhere you can look at it again. This is our come back to knowledge. When we get lost, come back to this. B to the x equals y. This is in an exponential format. Sometimes it's easier to work with it in a different format that's equivalent. That is called your logarithm format. Now, each of these have their advantages. If I'm in an exponential format, then I can easily find the anti-log. So exponential formats are best used in finding the anti-log. But logarithms, in that logarithm format, they're always used to find the exponent. They're best utilized, whatever I did, every time we're trying to find an exponent. You get the difference in the two? One format makes it very convenient to find the anti-log. That's this exponential format. If you already know your base and your exponent, just write it down, multiply them out, and get your anti-log. But there are times when we don't know that, so we're going to write it as a log format, and that log is going to be an operation that's going to permit us to find that exponent. Now this is a challenge at first, to get people over this hurdle, the stumbling block of the language, but there's not a lot of material here. I need you to think of a couple different things that will help you understand this language. A logarithm is synonymous with exponent. Logarithms really are exponents. When you hear exponents, you should also equate it back to logarithms and vice versa. The other thing I want you to keep thinking of is logarithms always equal exponents. That should help us translate. Now let's do some translations. There are three parts in all of this. If I go b to the x equals y, you should already know the names of all three parts. For instance, this x is the what? Exponent. This bottom number is always called the what? Don't think I heard it. Starts with a B.
Base.
Base. Base and exponent. What was a new word I threw out today? That's your anti-log. These three building blocks, these are the same building blocks you have to build with your log statement. It is a log of base B. This is your base. The base for the exponent is the same as the base of the logarithm. Now this is why I want you to remember that logarithms are always equal to exponents. Logarithms are exponents, because logarithms have to equal the exponent. What is the exponent over there? X. The only place that you have any room to grow now is your antilog. Yes. Here's your exponent, and here's your antilog. We have to be able to translate. Okay, so we're going to go do some translations. We got to do them quickly. Ready? I want you to translate this into a logarithm statement. It's going to be the same information, just written in a different language. So it's got to be a log of what base?
3.
Base 3. The base of the exponent will always be the base of your logarithm. And logarithms always equal what? Keep counting that. Logarithms always equal what?
Exponent.
Exponents. And what is the exponent? 4. The log of base 3 of our antilog 81 is 4. What this is saying, this 4 out here is the exponent I raised 3 to get 81. Same information, just in a different interpretation. This one. What log base do we have to have? 2. Of what number? 32. And it has to equal what value? Because 5 is the exponent I raised 2 to get 32. You got to learn to read it. If you can read it, you can understand it a lot quicker. It's the first step in the process. This one. It's a log of what base? 2. Log base 2 of what value? 1/8 is negative 3. We're saying that negative 3 is the exponent you raised 2 to get 1/8. Let's skip that one. Let's go to this one here. This is log of base 5 of 1 equals 0. See, once you learn to translate it, it doesn't change. The base is always the base, the exponent is always the exponent, and the antilog is always the antilog. It's just a matter of putting in the right locations. And this one's no big deal. It's log of base 10 of 1/10. 0.1 is negative 9. We need to be able to translate that direction, as well as translate this direction. So now we're going the other way. Sometimes it's better to write these in exponent form. So what does the log base 2 of 8 equals x translate into? 2 to the x equals 8. I bet you could tell me, using your mental prowess, what x is. Nice. Some of you are holding up with your fingers. 3. 2 to the third. 2 times 2 times 2. 8. We just solved it. You don't have to. I'm telling you to translate, but that is how you would solve it. Translate this one. It is. Can you tell me using your mental? 2. 2 is your exponent. 3 times 3 is 9. Let's jump down to this one. What do you raise 4 to get 1/4? X is a What do I raise 4 to get 4? What do I raise 4 to get 4? 1. It's 1 over, so it's -1. Yeah, some of you are stuck on -2. It's just -1. 4 to the first power is 4. And there's a couple things here. One left here. This says log of base. Oops, I'm going to exponential. So what's your base? 2 to the equals 0.5. I like it like this. 0.5 is a half. That helps me figure out that exponent has to be a -1. Okay, lesson to be learned here. If you do not have a log base, if they don't write it, it is 10. It's called a common logarithm. If you don't see it, it's 10. It's common logarithm. That's how they refer to it. So it's really 10 to the x equals 100. So when you see this, this is saying, what's the exponent you raise 10 to get 100? And x is 2. Okay, we're going to do this question 1. That's probably all we're going to get to. And then I'm going to modify your homework assignment because we didn't get to everything. I don't know how we did it in third period, but we made it through it all. It says, without using the calculator or using the computer or any technology of any kind, we should be able to find the value of these logarithms. So our first one is the log, and it's a common log, which means it's a log of base 10 of 10 to the 2.5. Now logarithms are always asking you to find the exponent. Now I'm just going to put in there x. What is the exponent I raised 10 to get 10 to the 2.5? And I always get these raised eyebrows on this, and I said translate them. What can I translate this into in exponent form? You just got done doing a bunch. What does this translate into? 10 to the x would have to equal 10 to the 2.5. Now, tell me, what does x have to be in order for these two values to be equal?
2.5.
X is a 2.5. No calculator is needed. Now, they do more of the same in these things. This is the log, common log of 100. They're really asking you to go find that exponent, but what's this base if you don't see it? 10. So I could translate this into 10 to the x is equal to 100. What does x have to be? X is 2. Can you do this one without any rewriting? What is the exponent you raise 10 to get 10,000? 4. What is the exponent you raise 10 to get 100? -2 is your answer. What is the exponent you raise 10 to get a negative point, yada, yada, yada? What do you raise 10 to get a negative 0.001? Thank you. Who said you can't? How come you can't? Ah, it's negative. Can you ever get 10 to a power to be negative? Think of that graph we did. It went like this. Did it ever go below? This is no solution. Whenever you see the log of a negative, what will you respond? No solution. Finally, there's a little bit of a exponent rule here. What is 10 squared times 10 to the 5th? So this says it's the common log of 10 to the 7th. What is the exponent you raise this 10 to get 10 to the 7th?
7.
So our answer is 7. Okay, so I got to modify. Here's what we're modifying. For tomorrow, I need this one done and that one done. That's the best we can do. That's going pretty hard and pushing pretty hard here. We'll do the rest of that assignment tomorrow then, with maybe a couple others added. But that's